Hello friends, this is Pallavi Kohli, student of ME315305. Today, in this tutorial, I am going to explain about the topic digital image and video coding. So, starting with what is a digital image? As we all know, digital image is composed of several pixels, where each pixel represents a dot of different color. So we can say that an image is a rectangular array or a matrix of n columns and n rows. So now the question arises, why do we need image and video coding? Unlike voice or text data, whose data is not that large, both the transmission and storage of image and video data are big issues. Since high resolution and high quality image and video results in large data size. In order to alleviate these problems, image and video compression play a very important role. Let us now discuss the image and video coding basics. The basic concept of image and video compression is redundancy removal. The types of redundancy are spatial, temporal, statistical, and visual redundancy. By using some mathematical algorithm and human visual system characteristics, the digital image and video information can be manipulated and thus can be represented in a compact way. Starting with transform coding. As we know, the transform coding can be achieved by using discrete cosine transform, which is also known as DCT, and discrete wavelet transform known as DWT. Transform coding forms the basis of image and video coding standards. This helps us to transform the image from the spatial domain to the frequency domain, thus providing advantage in terms of energy compaction and data compression. For example, JPEG selects DCT for its transformation and JPEG 2000 uses DWT, that is discrete wavelet transform. Let us now discuss discrete cosine transform in detail. This is a technique for converting a signal into elementary frequency components and plays a very important role in image compression. Consider an example of this colored image. As you can see, this is a colored RGB image. So the first step is to convert this image into YCB-CR, where Y component is for brightness and is a grayscale image, and CB and CI components contain color information. This whole process, it begins by dividing the Y image into 8 by 8 blocks, and DCT is applied to each block. One thing that we have to note here is that unlike Fourier transform, the result of the DCT is real number, so there is no need to store complex numbers. Also note that each block tends to be brighter than the upper left corner of the block. This is because the DCT coefficients have larger values, implying more information is contained within them. So, DCT compression allows us to throw away the information of less importance, thus providing considerable compression. Here, consider three different images. The first image is reconstructed with one coefficient, second with 3% of the coefficient, and the third one is constructed with 34% of the coefficient. So it is very difficult to see any difference between 34% image and the original because we have thrown away information that is of less importance for the human eye. The next step is quantization. As we all know, quantization is a process of converting a continuous range of values into a finite range of discrete values. In this case, it is used to control the compression ratio. By using quantization, the range of compression ratio is widened, thus providing better results. Entropy coding is used for lossless data compression, where the process can be divided into modeling and coding. Modeling assigns probabilities to the symbols, whereas coding produces a bit sequence from these probabilities. The two very common entropy coding schemes are Huffman coding and arithmetic coding. So the scheme that uses discrete number of bits for each symbol is Huffman coding. A different approach is arithmetic coding, which outputs a bit sequence representing a point inside an interval. In the end, we have motion estimation and motion compensation. These two schemes play a very important role in video coding to remove the temporal redundancy. Successive video frames may contain the same objects which can be still or moving. So motion estimation examines the movement of objects in an image sequence to obtain vectors that represent the estimated motion, whereas motion compensation uses the knowledge of object motion to achieve the data compression. So, this was all about image and video coding on the introductory part. Thank you.